Really wasn't expecting this no day today, but that's fine. This will probably be the last video that I'll have to make like this. So I'm going to try and get through this as fast as I can. This is, again, a little different than anything we've ever covered before. I kind of like this because it really sort of breaks apart how a chemical reaction happens. And this is why I like organic chemistry so much. There's a lot of mechanisms in organic chemistry where they talk about here's the step-by-step process for how the reaction actually occurs. Okay, so I think some of you are going to like this. Those of you who like to see, exactly how something works. So basically, a balanced chemical equation gives us information about the beginning and the end of the reaction. So if I have something like, CH4 plus O2 yields CO2 plus H2O. That tells us what happens, the reactants we had at the beginning and the products we have at the end. But it really doesn't tell us exactly how it gets from the reactants to the products, okay? Because if you think about it, there's going to be some breaking of bonds here with the CH4, some breaking of bonds with the O2 so that we can form the products. And the order in which that happens and how they rearrange themselves, the overall equation really doesn't give us a lot of information about that. And by the way, this isn't balanced, but I'm not going to take the time to balance it now. You may not have thought of that before. A chemical reaction really doesn't give you information about exactly how a reaction occurs. It just tells you, here's what we start with, here's what we end with. Okay? The reaction mechanism talks about how does it get from the reactants to the products, how exactly. Okay? So it's a detailed picture of which bonds get broken and formed. Elementary steps are those single steps that happen in a chemical reaction to get you from point A to point B. Okay? So elementary steps are usually defined by molecularity. Okay? So it's the number of molecules present in an elementary step. This is going to make more sense once I show you examples, so I'm just going to talk through this quickly. If it's unimolecular, that means there's only one molecule as a reactant in the elementary step. If it's bimolecular, it means there's two molecules in the elementary step. Termolecular is three molecules in the elementary step, and that's not very common because if you have, basically an elementary step involves the collision of certain molecules. So if you've got a unimolecular process, you only have one molecule as a reactant, so it's probably going to break apart. Okay. If you have a bimolecular, that's fairly common. You have two things colliding with one another, maybe a chlorine colliding with another chlorine to form Cl2. Okay, so that would be a good example of a bimolecular step where you've got two things that are colliding with one another and they're forming a product. Termolecular would have to be something like, a bad example. Well, it's a good example because this doesn't happen. O plus O yields O3, which is ozone. Okay? A termolecular would be all three of these oxygens collide with one another at exactly the same time. Now, the likelihood of that happening, not very likely for these three collisions to all happen simultaneously. Okay? And that's how it would have to happen to form the O3. So that's why the termolecular doesn't usually occur. Okay? Okay. So some reactions proceed through more than one step. We have these multi-step mechanisms. You're going to get a chance to write one of these in the lab that we're going to do at the beginning of next week. And I think some of you will have fun with this. It's kind of like a little puzzle that you have to figure out. So here's the overall reaction down here. Start with that. Now again, that tells you the beginning reactants and the end products. Okay? But maybe what really happens here is that you've got two NO2 molecules in this first step, and one of the oxygens in this NO2 gets transferred over to here. So now you have an NO3 and an NO, okay? And all that has to happen for that to occur is these two molecules have to collide with one another. An NO2 molecule has to collide with another NO2 molecule. And that's likely. That can happen, okay? So then you end up with NO3 and NO. All right, so then in the second step of the reaction here, well, maybe the NO3 collides with carbon monoxide, one of the other reactants here, okay? And then this oxygen in the NO3 ends up getting transferred over to the CO. So now you have NO2 and CO2. And again, this only involves two things colliding, so that's reasonable. And then one oxygen is just getting transferred between them. All right? So this is a mechanism that makes sense. Now, does it really happen this way? Ultimately, we're not sure. Okay? There's no great way to test for this. Okay, now what you can test for, if you have a way to test for this intermediate that appears in the reaction and then goes away. Notice NO3 is not anywhere in the overall balanced equation. All right, so if someone said, hey, I think this is the way that this reaction occurs. I think NO3 gets formed and then it gets broken down almost immediately by the carbon monoxide to form CO2. If they could prove that the NO3 was present at any point in this reaction, that would be a good way to show that they actually are right about their mechanism. All right, so if you could figure out a way to detect the presence of the NO3, then you might be able to say, yeah, my mechanism is probably correct. Okay, but the only way that you can really confirm these mechanisms is by doing experimentation. You can't know just by, because there are a lot of times for a reaction. Now, it might be tough with this one to figure out another good one, but sometimes you could propose more than one mechanism for a reaction, and they both might work out. Okay, you might be able to add all the steps together, and they might still add up to the balanced chemical reaction. So there are different possibilities there sometimes. It just depends on the reaction. And if there are different possibilities, then there's kind of debate oftentimes about, well, what is the actual process that this reaction takes to get from point A to point B? And sometimes that can actually be important. Okay. So here's the rules. Well, the main rule. If a reaction proceeds via elementary steps, then when you add the elementary steps together, it must add up to give the balanced chemical equation. So notice over here, if I add these two equations together, do kind of a Hess's law type thing, the NO3's cancel, right? One of the NO2's ends up canceling, and then you end up with NO2 plus CO yields NO plus CO2, which is exactly what we have in the balanced chemical equation. Okay? An intermediate is a species that appears in an elementary step that's not a reactant or a product. So our intermediate for this example over here would be the NO3. Okay, and we kind of already talked about that. It appears in the first elementary step, and it disappears in the second one, so it's like it was never there. Okay? In fact, it may never have been there if this is not the correct mechanism for this reaction. Okay? All right, so sample problem here. It's been proposed the conversion of ozone into O2 proceeds via two elementary steps. So remember what I said before. It's unlikely that you have O plus O plus O giving O3 because that's termolecular. So probably a more reasonable mechanism would be this one right here. Okay? So in the first step of this mechanism, actually this is the opposite of that. This is a breakdown of ozone. So the first step in that most likely would be that the O3, ozone, breaks down into O2 plus just oxygen. Okay? And then the second step there is that O3 reacts with oxygen, and then that's going to make two O2 molecules. Okay? So first thing we want to do is describe the molecularity of each step in this mechanism. Okay? So basically to do this, you have to look at the reactants. Okay? And in the first equation here, in the first elementary step, there's only one reactant. Okay? So we're going to call that unimolecular. What that means is there's not really any collisions happening here between molecules for this first step to happen. It just breaks apart. Okay? And that's what's going to happen with the unimolecular process. The second one, we have two reactants, two things that are colliding with one another to make this reaction occur. So this is going to be bimolecular. Okay? Write the equation for the overall reaction. All right, so if we're going to write the equation for the overall reaction, then basically we need to add these together, do a Hess's law thing here, and cancel out anything that that doesn't, that shows up on either side of the equation. So the oxygen here is going to cancel out, just the O by itself. All right. So then what we're going to end up with for the overall balanced chemical equation, we've got two O3s on the reactant side, and that's it. And then we end up with 3 O2 on the product side. Okay. So that's our overall balanced chemical equation for the reaction. And then identify the intermediate or intermediates. And the only thing that we have here that appears in the product side of the first step and then the reactant side of the second step is the oxygen, okay, just the O by itself. So the intermediate here is just going to be O. Okay? So the intermediate, when you're looking for the intermediate, you're looking for something that shows up, it's produced in the first elementary step, and then it's used up almost immediately in the second elementary step. So it's like it was never there. Okay? The intermediate will never show up in the balanced chemical equation. Okay. The rate law of an elementary step is determined by its molecularity. Unimolecular processes are first order, bimolecular second order, termolecular third order. Okay. So I'm trying to think of. This is where it gets a little bit tricky because I have already told you, to some extent, that you can't look at the balanced chemical equation and figure out the rate law. Well, kind of different for these. And actually, I guess I need to wait because we need to talk about the rate determining step. But when you're looking at an elementary step, you can actually look at the stoichiometry and you can tell the reaction order. Okay, so I'll show you kind of how that works as we go through this part. So the rate determining step is the slowest of the elementary steps. And the example I always give here, and they have a different example in the book. The example they give in the book works too. It's an example of a, I think it's a cars at a toll plaza, but I don't know. We don't have a lot of toll roads here in this part of Missouri, so that may not be in your realm of experience necessarily unless you've done a lot of travel. But something that probably is in your realm of experience is a fast food restaurant. Okay, in a fast food restaurant, you've got kind of two places when you're going through a drive-through at a fast food restaurant. There's kind of two places where you can get slowed down. Okay. One is where they take your order, okay? And then the other place is where they actually give you your food. So you're driving through, okay? And the first place is you place your order, all right? So let's say that at that first spot right there, the person who's doing the order placing is new. They've never done this before. They don't know how to punch things into their computer. And so you're doing your order, and they mess up a bunch of times, and they just have no idea what they're doing, and it takes forever for them to get your order right, okay? But then once you pull through, let's say the people who have been doing the food stuff for a while, so this is slow, but the people who have been, putting together your food, they've been doing that forever, and so as soon as your order goes through, they've got your food whipped up and ready to go, and so this is the fast step, okay? So your rate determining step, the step that determined how long your fast food drive-through experience took, was the first step, okay, the place where you're placing your order, okay? But you can imagine a reverse scenario here as well, where the person who's taking your order does it like a well-oiled machine, and so then, this is a very fast step, but then you end up sitting in the food, at the food window forever because they don't have your food ready, okay? So this is the slow step. So one or the other, when you go through a drive-through, is most likely going to be the rate-determining step. That's the slowest step of the overall reaction, okay? So a chemical reaction is the same way. If we've got two steps in a mechanism, for example, this one right here, okay? One of these steps is probably going to happen at a faster rate than the other. And depending on which one happens slowest, that's going to be our rate determining step, okay? In other words, that's the one that determines really how long the reaction takes to occur. So, maybe this is our slow step. It takes a long time for O3 to break down, but then once the O3 has broken down, the collision of an O3 and an oxygen, that happens very quickly. I don't really remember which one of these is the slow step and which one is the fast step. But if that's the case, the slow step is the one that determines the rate law, okay? So then, if I was going to write the rate law for this, now again, this could be wrong. I mean, the slow-fast part could be wrong, but let's say the first step is the slow step. Then my rate law for this one is determined only by this step, because it's the slow step. Okay, it's the one that determines how long the reaction actually takes. And this is just one O3 molecule. Okay, there's just a 1 coefficient there. So I can actually, when I'm looking at an elementary step, this is the key here, when I'm looking at an elementary step, then I can write the rate law for the reaction based on the stoichiometry of the slow step of the mechanism. Okay, so that actually would be the rate law for this reaction. Now notice the overall reaction here, remember, is 2O3 yields 3O2. Okay, now notice this rate law does not match the stoichiometry in the overall reaction. It only matches the stoichiometry in the slow step of the mechanism. Okay, so you have to be careful with that. So what I've told you before is the rate law has to be determined experimentally. That's still true because we still have to do experiments to figure out if this mechanism is even actually correct. Okay, so you can propose this mechanism and fine, maybe it works on paper, but it may not work in real life. So then you have to go and confirm that with an actual experiment. Okay, hopefully that all makes sense. So if you have a unimolecular process, you have A going to products. The rate law would be rate equals K times the concentration of A, right? You've got a bimolecular process, then you've got A plus A. Now the way that that's usually going to be written in a chemical reaction is just going to be 2A, the coefficient 2 in front of it, okay? So that 2 becomes the exponent in the rate law for a elementary step, okay? You might have A plus B, okay, then your rate would be rate equals K times A plus B, coefficient 1 for each of those reactants, so there would be an exponent of 1 on each of the reactants, okay? Then you've got your termolecular processes, again, way less common, but you could have A plus A plus A, all three of those colliding at the exact same time, so then your rate law would be third order overall, okay? And so on and so forth. Okay, if the following reaction occurs in a single elementary step, predict the rate law. So, and this is reasonable because this is one molecule, this is one molecule, so we've got a bimolecular process happening here where two molecules collide, and then you end up with a product, okay? There could be a different mechanism that you could propose here, but let's say that this all happens in one elementary step. So basically what you've got here is an A plus a B situation happening, okay? So then your rate law for this one would just be K times H2 times Br2. And because there's a coefficient 1 in front of the H2 and the Br2, then you just have an exponent 1 on both of those, okay? And again, you can only do that if it's an elementary step. You can't do that if it's an overall reaction where there are multiple steps in the mechanism. Okay, if experimental studies of this reaction show that it has the rate law, rate equals K times H2 times Br2 to the 1/2, what does that tell us about the reaction? Well, it should tell us that the reaction doesn't happen in just a single elementary step, okay? So we made a bad assumption thinking that it happens in a single step, because this is, once we do an experiment and we figure out this is the actual rate law, okay, that would tell us that the mechanism here that we proposed is wrong. We need a two-step mechanism at least, okay, to explain how this reaction occurs. So again, that's why we have to do the experiment, because we can propose a mechanism that looks good on paper, but it may not be what's really happening in real life. Okay, rate determining step is the slowest step, so that governs the overall rate law for the reaction. I talked about that with the fast food thing. So here's an example. It's found experimentally the rate law for the reaction NO2 plus CO yields NO plus CO2 is, and then it gives this rate law, K times NO2 squared. So what's a reaction mechanism consistent with this rate law? Okay, I don't expect you to know how to do this yet. We're going to get some practice with this when we do the lab that we do on Monday. writing your own mechanism. And it's kind of fun, like I said. I don't think you're going to probably have to do anything this extreme on the AP exam. I don't think they're going to expect you to write your own mechanism, but I like to have students practice it at least a couple of times just because I think it does a good job of showing you what a mechanism actually is. Okay? So what we've got here, this is our overall reaction. And we've got to figure out in a certain number of steps, could we propose a couple of elementary steps here that maybe will get us from point A to point B? Okay? We could say, oh, well, I think that this NO2 just collides with the CO, and then all of a sudden we have NO and CO2. Okay? Which, you know, is not outside of the realm of possibility entirely. I mean, you could have one of these oxygens transfer over here, and then you end up with NO and CO2, right? Problem is that doesn't match our rate law, because if this was our only step of this reaction, if this was our elementary step, this is a coefficient 1 right here, and this is a coefficient 1 right here. So our rate law for this reaction, if this just happened in one step, would be K times NO2 times CO. And that does not match our actual rate law here. Okay? So we've got to come up with a mechanism that actually matches the rate law for this reaction, the experimentally determined rate law. But by the way, I should back up maybe and talk about how do we experimentally determine that, just to remind you. That goes back to stuff that we were talking about several days ago, where basically you just, in this reaction, you maybe start with a 0.1 molar concentration of this, and a 0.1 molar concentration of this. It may not make sense to talk about this in terms of concentration. It's probably pressures. So let's say 1 atmosphere of pressure here, 1 atmosphere of pressure here. And then in the second experiment, we would do 2 atmospheres of pressure of the NO2 and hold this steady at 1 atmosphere of pressure. Okay? So let's say that the rate of the reaction, and I'm just making up easy numbers here, was 2, okay, for this one. For the second one, because this is NO2 squared, when we double it, then we quadruple the reaction rate, so now it's going to be 8. Okay? And then we would also find by doing the experiment, if we doubled the, maybe we take this back down to 1 atmosphere and double the pressure of the CO, and notice it doesn't make any difference whatsoever. Okay? So then we would realize, okay, so CO shouldn't be a part of the rate law, but NO2 should. And that's how we determine that experimentally. Okay, so moving on. What we need is we need one of our reactions here to actually, one of our elementary steps to just involve NO2 as a reactant. Okay, so in order for this to work, one of our elementary steps has to just be NO2 as a reactant. All right, so it's got to be unimolecular. But it needs to have a coefficient 2 in front of the NO2. So let's see if we can make that happen here. Maybe NO2 breaks down into NO and O2, oxygen. Seems like that could happen, right? But again, in order for you to have O2 here, this is not a balanced chemical equation. Now it's a balanced chemical equation, okay? So now we've got 2 NO2s breaking apart to form 2 NO, nitrogen monoxides, and an oxygen molecule, okay? That seems reasonable, okay? Then maybe in the second step, that O2 that formed in the first step could react with the CO to form the CO2, okay? Now again, this is a little tricky, and you got to take some time to think about it, and you probably wouldn't have come up with that just right off the top of your head, okay? And again, this isn't balanced yet. Let me balance this second one. So 2 there, 2 there. Okay, I think we got it now. Now, there's 2 steps here, okay? The rate law is based on the first step of my mechanism. So assuming that my mechanism is correct, this would have to be the slow step, okay? And this would be the fast step. If my mechanism is correct and the first elementary step is the slow step, then that would give me the right rate law, okay? Because I've got a coefficient 2 right here, and I've got an exponent 2 right here, okay? So again, that's a little tricky, and you're going to get some practice with that on the lab that we do, trying to figure out a mechanism for a reaction, it can be kind of fun. All right, what if the reaction in the previous example happened in one step? Would that still be consistent with the experimental rate law? We already talked about that, so I'm going to move on. Okay, here's where it gets a little bit weird. It's possible for an intermediate to be a reactant. So consider this reaction, okay? The experimentally determined rate law for this reaction, this overall reaction right here, is K times NO2 squared times Br2, okay? But let's say that this is the mechanism that we have for that reaction, okay? To assume that this happens in a termolecular, that all three of these, this NO and collides with another NO at the exact same time that it collides with the Br2, that's not entirely likely, okay? So probably the mechanism for this reaction is a little bit different, even though really this rate law does sort of match this overall reaction, okay? It's much more likely that there's something else going on here. So the proposed mechanism for this one is that maybe the NO hits one of the Br2s first, okay, and forms this intermediate NOBr2. And then the NOBr2 reacts with NO to form the NOBr, okay? To form two of the NOBrs. All right, so that involves two bimolecular steps, and that just seems a little bit more likely than all three of these molecules, you know, having an NO, and a Br2 all collide at exactly the same time, okay? Just not all that likely. So that's why this other mechanism is proposed, okay? Now here's the problem, though. Notice on this one, the slow step is the second step. So if I wrote my rate law based on the second step in this reaction, my rate law would be this. Rate equals K times NOBr2. Oh, ran out of room. Sorry, I'm going to have to put this other one in the next line. Times NO. Okay? And that matches this second step in the mechanism. But that's strange because if you write that rate law for this overall reaction, then the question people are going to ask is, where did NOBr2 come from? That's not even in the equation, all right? So the rule is, in your rate law, you cannot put an intermediate. Because, and the main reason is, this is a proposed mechanism, right? We don't even know if this mechanism actually is how it occurs. So this NOBr2 is kind of theoretical, right? So you don't want to put something theoretical in your rate law. That's just not a good idea, okay? So you can't have an intermediate in your rate law, so that gives us a problem with this mechanism. But there's kind of a way around this, and the way around this involves equilibrium, okay? Now, here's where it gets a little bit tricky, okay? Equilibrium means that a reaction is happening forward at this exact same rate that it's happening backwards, okay? So here's the rationale on this one. And you know, we can talk about this more in class if you need to, because this is a little bit tricky. And I don't even know that this is going to be on the AP exam anymore. I have seen it on previous AP problems, so I'm going to cover it just to make sure. Seems like the way they're wording the new curriculum that maybe it's not going to even be on there, okay? But basically you've got this mechanism, okay? And maybe in this first step, this NOBr2 gets formed, okay? So that's the fast step. Now, everything comes to a screeching halt on the second step where the NOBr2 starts to react with the NO. Well, that takes a long time, all right? So actually what most of this NOBr2 is probably going to do is just go ahead and turn right back into NO plus Br2. All right, so because this is the fast step, instead of the NOBr2 mostly reacting here, you could say that the rate of the forward and reverse reactions on this first reaction, on this first step here, are going to be equal to one another, okay? So basically, you've got a reaction rate going forward, a reaction rate going backwards, okay, K1 and K to the negative 1, because it's the opposite rate. But basically, those are happening at the same rate, okay? So that helps us with something here. Okay, so this is just basically what I was just talking about. If you took the rate based on the second step, NOBr2 times NO, but that's not a good idea. We shouldn't. Intermediates are unstable. We don't even know for sure that that mechanism works, so we don't want to put an intermediate in the rate law. Okay. So assuming that this NOBr2 is unstable, then we can express that NOBr. We can basically do a substitution is what we can do here. That's the trick. Okay. So the NOBr2, I can write that instead as K1 over K minus 1 times NO times Br2. Now I have to go back and kind of show you how that works. Okay. So if I'm writing the rate law for this forward reaction on the first step, the rate equals K times NO. Well, okay, K1, because they labeled this as K1 for the forward reaction. K1 times NO times Br2. Okay? For the second one here, not the second one, but for the backwards reaction on this one, okay, going back this way, the rate is K to the negative 1 times just NOBr2. Okay? Now, those are my two rates with my two different rate constants. Okay, but remember what we said about this, if it's at equilibrium, and we've done this before. I should mention this. So you've got a beaker, right? You've got some water molecules down here. And this is a closed, it's going to need to be a the amount of, shouldn't say the amount, sorry, the rate of the evaporation is equal to the rate of condensation once you reach equilibrium vapor pressure. So both things are happening, but the rates are the same, all right? So what I'm telling you is in an equilibrium, the rates are going to be equal to one another, all right? So we can actually set these two equations equal to one another. K1 times NO times Br2 is equal to K to the minus 1 times, ran out of room, sorry, NOBr2. That's ugly. Let me try that again. Times Br2 is equal to K to the minus 1 times NOBr2. All right. Now, K1 and K minus 1 might not be the same number. Okay. The rate constant for these two reactions might not be the same. But we just label them as K1 and K minus 1 to show that one of them is the rate constant going forward, the other one's the rate constant going backwards. Okay. But we can solve this thing in terms of the NO and the Br2 so that basically we can do a substitution. So if I divide both sides by K to the minus 1, then I end up with, okay, my NOBr2 concentration is actually equal to K1 over K minus 1 times NO times Br2. All right? Well, what I have here is two rate constants. Okay? Two rate constants equals a rate constant, right? So, I mean, these are both just constant numbers, so you take one divided by the other, you end up with a constant. Okay? So, that's how we end up with this that they just showed you. Okay? That's just showing you the derivation for that. Now what we can do, this was our rate law that we originally wrote, okay, based on the slow step in the reaction. But because we're not allowed to have an intermediate in that rate law, let's just go ahead and substitute in this for NOBr2. Okay, so we just plug that in right there. Okay. And so then what we end up with is this expression right here. The rate equals K2 times K1 over K minus 1. That's supposed to be an exponent. No, I guess it's not. Okay. Times the NO2, or sorry, times the NO squared times the BR2. Okay. That's consistent with the experimentally observed rate law. Okay. Because basically you take this whole mess right here, K2, K1, K minus 1, multiply all those constants together, and then you just end up with a constant K. All right? Okay. That's a little tricky. Again, if you need some help on that, we can talk about it in class. But if they have an initial fast step, oh, is this an example? I think this might be an example. And I'm going to have to cut this off pretty soon because this video is getting really long. Yeah, so your slow step on this one has an intermediate in it. Okay, so this is another practice basically just like the last one. Okay, so what you'd have to do on this one, and I'll just walk you through it very briefly and then we'll end. So you've got your N2 O2 here. Your rate law for this reaction would be K, times N2 O2 times Br2, right? But again, N2 O2 is an intermediate, shows up here, goes away here, so it doesn't even show up in the overall reaction. So you don't want that in your rate law. So what you have to do is basically substitute the N2 O2. You're going to end up substituting the NOs in for it, okay? Now you just basically take it through the same process as we just did on the other one, where you say that you write the rate law for both the forward and the reverse reaction using the K1 and the K minus 1, okay? And then you realize that the two rates are equal to one another, so you can set those equations equal. You solve for the N2 O2, and then that will give you the rate in terms of the NO instead of the N2 O2, okay? And then you can just plug that in, and then you should get a good rate law for that one, okay? All right. I think this is an example they give you in the book, so, but just in case they don't, I guess the answer you're looking for on this one should be, once you've worked it all out, your rate should equal K times NO squared times Br2. Okay, that should be your rate law after you've worked it all out. Wait, is that what we just did? No. So a different mechanism, it looks like. Yeah, because this one doesn't involve NOBr2. This one involves N2O2 instead. Huh, interesting. Okay, so this it shows you there's more than one mechanism for any particular reaction. All right? Okay, again, sorry about the length on this one. I needed to make sure and go through this in detail, especially since you guys haven't been here for a few days. So we will see you in class tomorrow. We'll have a quiz tomorrow on 14.1 to 14.3. So don't worry about this new stuff for a little while. We'll figure out when to take the quiz on that. Okay, see you in class.